day. New day, a new chapter. Today, we move from energy to momentum. Two things that are both conserved, but we're often confused one for the other. What's the difference between momentum and energy, kinetic energy, for example? We want to always kind of relate inertia and momentum, but they're not necessarily the same exact thing. They're both manifestations of the mass. But inertia is something that inertia is something that is inherent to an object with mass, and the object always has it. It always has the same amount of it. Whereas momentum is only something that an object has if it is moving. And that momentum can be transferred from one object to another. So both of them are related to mass, but they are not the same thing. But momentum is very much like energy in that it is conserved. You cannot create momentum, you cannot destroy momentum. In fact, momentum is even more conservative than energy. Because of Einstein's discoveries, we learned that energy can be converted into mass, and mass can be converted into energy. So you kind of can destroy energy by turning it into mass. And you can kind of create energy by destroying mass. So, but momentum is not that way. Momentum is one of the absolute conserved quantities of the universe. As far as we know, there is no situation that we have observed in any kind of scientific situation where momentum is not conserved. What's that?
Right.
So, we're going to start off by talking about linear momentum, and here's the definition. The definition of linear momentum is the product of the mass and the velocity. Of course, the mass is just a scalar quantity, but the velocity is a vector. So the momentum ends up being a vector. And this is another one of the major differences between momentum and energy. Remember that energy was not a vector. Energy didn't have direction. It could be positive or negative. It could be energy taken from the system or energy put into the system. But it didn't have a direction associated. It wasn't going some, north or west or X or Y or whatever else. Momentum does have a direction. It is going a particular direction. So momentum has a magnitude and a direction, just like velocity, just like displacement, just like acceleration. It is a vector. And I told you we wouldn't be dealing with vectors very much anymore. Well, this is that time. There's the reason that I didn't say we wouldn't be dealing with them at all anymore. This is the vector. The final vector we'll be dealing with in this semester. Momentum. So let's calculate some momentum. We have a 110 kilogram football player running 8 meters per second. Compare the player's momentum with the momentum of a hard thrown ball that is 0.410 kilograms at a speed of 25 meters per second. So the momentum is the mass times the velocity. We're just going to calculate the magnitudes. We're not going to worry about directions. Just the magnitude of the momentum of the player is 880 kilogram meters per second. It does not have its own unit. It's just kilogram meters per second. The momentum of the ball, even though it's moving 3 times faster, is only 10.3 kilogram meters per second. Right? What does that mean practically speaking? Momentum is the thing, or it's one of the things, one of the major things, that causes movement to transfer from one object to another. So it causes one object to push another object because they collide, for example. So if you see a movie You see this all the time in sports movies where somebody catches a football and throws them backwards or knocks them down. Well, compare these momentums. The momentum of the person is nearly 1,000 kilogram meters per second. The momentum of the ball is 10 kilogram meters per second. It's just barely 1% of the momentum of the person. Not likely to move the person very much. Well, it turns out that Newton's second law of motion can be described in terms of momentum because momentum is mass times velocity. If you divide velocity by time, you get acceleration. And so if you take momentum and divide by time, you get mass times acceleration, which is force. So your momentum, your change in momentum divided by a change in time, in other words, how much momentum changes over time, will tell you how much net force was applied. Pretty simple. So that's Newton's second law in terms of momentum. If you want to do that, if you want to work that out, this is how it looks. Change in momentum is change in mass times change in velocity. If your mass doesn't change, then you can just take that out, and it's mass times change in velocity. Change in velocity over change in time is acceleration, so that force equals change in momentum over change in time also equals mass times acceleration, what we just said. So, here's Venus Williams' fastest recorded serve in premier women's match, 58 meters per second, 209 kilometers per hour, 30 miles per hour, something like this, 140 meters. We want to know what kind of force was applied to this by using the change in momentum. So force is change in momentum over change in time. Change in momentum is mass times change in velocity. The mass of the tennis ball is 0.057 kilograms, and this happened over a 5 millisecond time period. The ball went from 0 to 209, or from 0 to 58 meters per second. So our final velocity is 58 meters per second. Our initial is 0. Plug those numbers in down here. Plug in the mass. You get a change in momentum of 3.306 kilogram meters per second, and divide that by the time that it took, which was the 5 milliseconds. 5 times 10 to the minus 3, you get 660 newtons. Right? So that's significant, 150 pounds of force or something like that. Now a new concept. Change in momentum. We're going to give change in momentum a name because it's associated with force. If we take this equation, force net equals change in momentum over change in time, and rearrange it to be change in momentum equals force times change in time, then we get this thing, this change in momentum thing, which we're going to call impulse. An impulse is a change in momentum caused by a force over a particular amount of time. It's kind of like work equals force times distance, but this is now momentum equals force times time, right? So this is what we call an impulse. So let's calculate the magnitudes of two impulses. We have one billiard ball that's striking a wall head on and bouncing straight back. The other one bounces at an angle. This is what it looks like. One ball comes in, hits the wall, comes back out. The other one comes in at this angle at 30 degrees. Bounces out. Right? We want to know what is the impulse or the force on the wall because of this impact. Now this is something we've never done before. We've never really converted a velocity into a force. But remember, it's not just a velocity, it's a change in velocity. And a change in velocity, if we know the time, is also an acceleration. So then we can start to calculate a force if we know the mass, because we know that mass times acceleration equals force. Let's go ahead and do it. Our initial momentum of the ball coming into the wall is mass times velocity. Now we're using u for velocity here. don't be confused or upset by this. They're just using it because they don't want to use V for everything and get confused from one thing to another, just whatever. So they're using U instead of V. I think it's dumb to do that, but they do it anyway. So they're using U to be the speed of each ball before and after the collision with the ball. M is the mass of each ball. So there's our general equation. The initial momentum in the x direction is going to be mu times U, m times U. And the initial momentum in the y direction for the first ball is 0. So this one is going to be the first one. They're actually pointing in the other direction, so the ball is coming in this way. So this is the x direction. This is the y direction. So the y direction is 0 for the ball that comes straight in perpendicular to the wall. It has no y direction initial momentum or final momentum, but it's in x initial momentum and final momentums are defined here. M times U, and then negative m times u as it comes out, because it's going the other direction, right? So that's its final velocity is negative u, and that is the initial and final momentums for the first ball that comes in perpendicular. However, for the ball that comes in at an angle, the x momentum is going to have a cosine 30 degrees in it, because only the x part of the velocity calculates into the momentum. So momentum does depend on angle, it does depend on direction, right? So it looks different here, and then you have a y momentum as well. Notice that the y momentum stays the same. Why does it stay the same? Well, the second one looks like this. I should do this on the computer, because I'm recording this class. Okay, let's see. Okay, so here's our wall. Here's our first ball, comes in with this velocity u. Remember that they gave it a u instead of a v. U initial, and that's all in the x direction. And it comes out with a final velocity, u final, which is negative, u initial. It's the same u, same velocity in and out, except different directions. So it's a negative on the way out. So its initial momentum is m times ui. Its initial momentum in the x direction. And its final momentum in the x direction is negative mu u times m. It's its final momentum, right, in the x direction. Fx. Anyway. Initial final. But if you're coming in at this angle, 30 degrees, then you have your x part of this. Let's see. I think this is their 30 degrees. Yeah, so they're doing 30 degrees to the normal. But anyway, your x part of this is this part of your velocity, right? Is that right? Yeah. So that's your x part. It comes in this direction, it comes out this direction. But your y starts off going down, and it ends up going down, right? This is your yu, u sub y. It never changes. The bouncing off the wall doesn't change its direction up and down. So in other words, the change in momentum in the y direction is 0 because the change in velocity in the y direction is 0. So it doesn't get affected. But the change in momentum in x is this momentum initial in x minus this momentum, or sorry, the final one in x minus the initial one in x. And those two have a cosine, so they end up being u x m cosine 30, right? And the other one's negative u x m cosine 30. Anyway, so that's what you get here. For the x ones, you get these things with the cosine 30. For the y ones, you get the same thing in each one, mu sine 30, negative mu sine 30. But when you take the difference between these two, it goes to 0, and there's no change in momentum in the y direction. So When you take the differences for both of these, for this one you get 2 times m times u. For this one you take negative 2mu because you start off with final minus initial minus mu gives you minus 2mu. So in other words, your change in momentum is equal to twice your initial momentum. Whereas this one ends up being 2mu over, this one ends up being 2mu times cosine 30, negative 2mu times cosine 30, which is less than 2mu. So the one that's at an angle has less of a change in momentum than the one that comes in straight. So hopefully that makes sense. If you throw something directly at a wall, the wall will impart more momentum to the thing that you threw at it and it will come back faster. But if you throw it at an angle, it's less and less momentum the more and more angle that you throw at it.
Does that mainly due to the normal force pushing back, like after the impact? Not the normal force, but the bounce back, basically.
Yeah, it is the normal force as it comes in contact that pushes back. That is correct. That's what's causing this change in momentum. That is the force. Let's see, let's get rid of this one. Now, conservation of momentum. Just like with energy, as people were doing experiments with objects colliding with each other and exchanging momentums back and forth, they noticed that the overall total momentum of a system is conserved as long as there are no external forces. As long as there are no forces on the outside of the system that transfer momentum out of the system, the momentum within the system of interest is conserved. So, you have two cars, one that has mass 1, another one with mass 2, and one of them hits the other car. So the second one hits the first one hits the second one. The second one is going to go faster, and the first one is going to go slower after they collide. Right? Some of the momentum of the first car transfers into the momentum of the second car, and the overall momentum will be the same still. How much of the momentum transfers? Well, that depends. What does it depend on? Of course, it depends on mathematics. So, change in momentum of the first car equals force 1 times delta t. Change in momentum of the second car equals force 2 times delta t. But if they collide, force 1 and force 2 are equal because of Newton's third law, right? Any force that is exerted on one thing, the one thing exerts the same force back on the first thing, right?
So you have to calculate the force first. How do you calculate the force?
You don't even have to calculate the force. All you have to do is recognize it's the same force for both cars. And once you do that and know that it's the same force for both cars, you will know that it turns out that these two things have to be equal and opposite, and they have to add to 0. That's the whole point. You don't ever have to even calculate the force. Just knowing that it's the same force for both of them, you can set these two equations equal. That ends up showing that one of them is equal to the negative of the other, and when you add something and its negative together, you get 0, which tells us that the change in momentum of the first car plus the change in momentum of the second car has to equal 0 every time. So if this car loses 5 kilogram meters per second of momentum, then this one has to gain 5 kilogram meters per second momentum. And that is an absolute law of nature.
Yeah, but they're not going to tell us the force.
Nope, not going to tell us the force because we don't need to know the force. That's the beauty of it.
All right, but what do they want to tell us?
We're just going to mess with the momentums now. Momentums are easier than forces. Isn't that beautiful? We'll show you in a second. The whole point to understand here is is that this is absolutely true. There has never been an instance where this has not been shown not to be true in any situation. This is absolutely true as far as we have ever observed. Okay? So momentum transfers back and forth between objects that exert forces on each other. If you exert a force on something and it changes its momentum, your momentum will change in the exact opposite direction with the exact opposite change in momentum. Okay? So it is absolutely true. You don't always notice it. For example, when you push on the earth to walk forward and you change your momentum to walk forward, you do change the earth's momentum and the earth will walk backwards. The earth will rotate backwards. But it's so small and there are so many different people walking on the earth that it all cancels out and you never notice it. If there was one person on the earth and they walked in any particular direction on the earth for their entire life, it would hardly make a difference to the rotation of the earth because the earth's momentum is so much bigger than the momentum of the person. But it would make a difference. So, one of the results of having one of these conservation equations is that if you change this from a change in momentum plus change in momentum to momentum 1, momentum 2, momentum initial, momentum final, whatever else, then it tells you that you can add up all the momentum in the system at any given point in time, and it will have to equal all of the momentums at any other given point in time as long as no external forces have transferred momentum in and out of the system. Right? So the total momentum is always the same throughout an isolated system. Now here's an interesting situation. We have a rocket that's taken off from the ground and now its rocket is no longer firing. If the rocket was still firing its gas out the back, then that would be an external force that's transferring momentum out of the system. In other words, the gas leaving the rocket would be taking momentum out of the system. But it's no longer firing and it's just in projectile motion. But while it's in projectile motion, the top of it comes off and it explodes off upward using some kind of, something. And it goes this way and this rocket goes down this way. And we're going to consider this our system of interest. And this is still our system of interest even though it's two different things. We can actually calculate how fast one of these things is going if we know how fast the other one is going in the mass of both objects. It's not that hard to do. It's just a matter of conservation of momentum. The same happens with subatomic particles and all kinds of particles and everything. And this is actually how we do science at the subatomic level, where we can't actually see the particles, at the atomic level, where we can't actually see the particles. How do we do it? We measure their momentums. That's something we can measure. Even though we can't see an atom of gold, we can measure its momentum. Okay? How do you measure its momentum? You run it into something. You run it into something and you measure how much force it exerts. And that force over the amount of time that it took for that force to exert itself times the amount of time is equal to the change in momentum. So you can learn a lot about these things just by colliding them and observing how they move, observing their recoil, observing their change in momentum. So now we're going to study this and try to understand it the best we can using a great tool for this, which is collisions. We're going to study two different kinds of collisions, neither of which is neither of which really exist in nature, except at the subatomic level. At the atomic level and below, we have a thing that's called an elastic collision, which is a collision where all internal kinetic energy in the system is conserved and all momentum is conserved. That does happen at the atomic level and below. Small things do that all the time. No energy is lost in the collision. But in real life, energy is lost to some degree. And so we also try to study another type of collision, which is called the perfectly inelastic collision, where kinetic energy is not conserved. Momentum is still conserved, but the two objects that collide will become one object. They will stick together, which never absolutely happens either, but we can get pretty close to that. You know, if two objects stick together, it's good enough. They become one object. It's good enough to call it an inelastic collision. We'll start off with the elastic collision. Conservation of internal kinetic energy is within our system is going to take effect, and conservation of momentum. So here is an object, two objects that are going to collide elastically. Why do we call it an elastic collision? Because in elastic collisions, with an elastic collision, the two objects will bounce off of each other perfectly. There will be a perfect bounce with no loss of energy in the bounce. Okay? So where do you see that? You can kind of see it on an air track with magnetic bumpers. You can kind of see it on one of these tracks with the magnetic bumpers on the cars. Those are fairly good elastic collisions. They're not great, but they're fairly good. You really see it at the atomic level. But there's going to be a perfect balance here. Nothing is going to stick together. No energy is going to be lost. No sound is going to be made. Nothing's going to deform. So here we go. But whenever you have a system like this, you're going to have your total momentum is going to be the same at the beginning and at the end. And the total kinetic energy at the beginning and at the end is going to be the same. So these two equations are going to be true. And in the end, you can solve these two equations. Total momentum beginning, total momentum ending, total kinetic energy at the beginning, total kinetic energy at the end equal. And you have two sets of equations. You have four things you don't know. Mass 1, mass 2, velocity 1, velocity 2. Those are four things you don't know, but you only have two equations. So in order to solve this system of equations, you're going to have to know two of these things. You're going to have to either know both masses or both velocities, or one mass and one velocity, or whatever. But you're going to have to know at least two things, because you have to have the same number of equations as you have unknowns, right? So let's do an example where they give us some of our knowns. And actually, we have 6 unknowns, 2 masses and 4 velocities, because we have initial and final. So you have to know 4 things. You have to know at least 4 things. In this problem, we have an elastic collision, and they tell us the masses, and they tell us the initial velocities of both objects. The first object is going 4 meters per second. The second object is stopped. Right? So we know 4 things of the 6, so we should be able to solve. The first equation tells us that the momentums at the initial part have to equal the momentums at the end. And since the second object has no momentum at the beginning because velocity 2 is 0, this is what the equation looks like. The second equation, the conservation of kinetic energy, is going to look like this: 1/2 m1 v1 squared. That's the kinetic energy of the moving, whatever it is. And then the two final kinetic energies, but the second initial kinetic energy is 0, right? So we have a second equation that looks like this. So we have two equations, this one right here, which looks like this, and this one right here. So these two equations we can solve to get the things we don't know. If we solve the first one, for velocity 2, this is what we get.
That velocity prime.
Yes, velocity prime is final velocity. So velocity 2 final equals mass 1 over mass 2 times velocity 1 minus velocity 1 final. Right? However, this doesn't give us an answer because we don't know either of the final velocities. But we can plug this one in to this equation and get an answer. If we do that, we're going to get two answers because it's a quadratic. You plug this in, it's going to be a big messy quadratic. You'll have to solve it using the quadratic formula, and you get these two answers. Well, then you just got to choose. Choose one and try to solve for the next one. Let's see. Yeah, so in the first one, the first answer in this, V1, is 4 meters per second, but remember what was our first initial velocity for the V1? It was 4 meters per second, right? If we had a stopped thing and a moving thing initially, and then the moving thing hit the stopped thing, it would not be going the same speed afterwards, right? It would definitely change speed. So it's not, doesn't make any sense for the velocity of the first object to still be going 4 meters per second after it's already hit something. You know, so this one doesn't make any sense. They say it's the initial condition, but that's what that means. It started at this speed, it can't still be going this speed. So this is the only one that makes any sense. So they go ahead and use this one, and they plug this one back into one of these equations, doesn't matter which one. To get V2, I would plug it into this one. You get V2 prime, and then once you calculate V2 prime, you get 1 meter per second and you're done. So what happened here? We had an object moving along at 4 meters per second. It hit a second object. It bounced off the second object and ended up going backwards. And the second object ended up going forwards at a very slow speed, which makes sense because the second object was more massive. If you have a fast-moving small object hitting a stopped big object, that's what happens. The small object bounces off and moves backwards, and the big object moves forward slowly, right? That's what we would expect.
And it looks like it's part of 1/4 of its momentum onto the object that's sitting still.
Well, that's a good question. If you want to talk about fractions, you have to actually look at the momentum. Right here, you're looking at the velocity, not the momentum.
Or not.
Yeah.
Velocity, sorry.
The second object ended up with 1/4 of the initial object's momentum, velocity, but not necessarily momentum, because momentum is mass times velocity, right? The mass of the first one is 0.5, so 0.5 times 4 is 2 kilogram meters per second, and the second object ends up with 3.5 times 1, which ends up being 3.5 kilogram meters per second. So it actually, the second object actually ends up with more momentum than the initial object had. But the initial object ends up with negative momentum. So if you add up the final momentum of the big object and the final momentum of the small object, they will cancel out to be the initial momentum, which is 2. It'll end up being 3.5 times 1.5. But 3.5 minus 1.5.
That's a low computation. I don't want to read it.
Okay, well, let's draw a picture out and show and explain to you. I like the way you said that. It's a lovely dictation, but stop talking now. Right? Isn't that what you meant?
Oh, well, maybe.
Yeah. Stop talking and draw me a picture, man. All right. Let's draw a picture of this. So, here's the situation that we had. Let's use cars. So we had 2 of these cars that we use on our little tracks here. One that was moving and had a mass of 0.5 kilograms. And it was moving at 4 meters per second. That means its momentum, this is mass 1, the momentum of 1 was 0.5 times 4 meters per second, which is 2 kilogram meters per second, right? That was its initial momentum. The second car was sitting still at 0, right? It was sitting still at 0, so its momentum of car 2 is 0. But its mass is 3.5 kilograms, right? So this has a much bigger mass than this one. In fact, we should just draw it bigger so that it looks bigger. It's a bigger car, right? Here we go. So this little tiny car is moving pretty quick. This big car is not moving at all. After they collide, what happened? Well, the big car starts moving forward, but just really slow. Instead of having a great big vector like this, it has just a tiny little vector at 1 meter per second. Right? It's still this great big mass at 3.5. But the little car bounced off and went backwards at almost the same speed as it was going before. Not quite, but almost as fast as it was going before, but backwards now. 3.5. Was it 3.5 or 1.5? 1.5. Here we go. 1.5. Was it 1.5? What was it? Can't
It was
even
going
remember.
backwards as
The two or three? Or three. 3 meters per second. So it's going backwards almost as fast as it was going forwards. Still, but it's just this tiny little thing, mass of 0.5, right? Is this what you would expect? So let's do an experiment. What kind of heavy things do we have and light things do we have in here? I have a perfect example. I have a little tiny ball here, and I have a big ball here. You guys done this experiment before? So the big ball and the tiny ball are going to have a collision. I'm going to affect this collision in a funny way. I'm just going to drop them both together and let them hit the floor together. But the little ball is going to be on top of the big ball. As this happens, what do you expect to happen? Right? The big ball hardly moves at all. This one goes flying off again at a high speed, right? That's a conservation of momentum issue. Going down, they had the same momentum, but when they collided with the ground, the big ball had very little reaction to it. It did have a reaction, but the little ball had a huge reaction to it, right? And the reason is because the little ball has a small mass, the big ball has a big mass. Right? And the same thing happened here. We had a small mass with a lot of speed and a big mass with no speed. The little mass, when it hit the big mass, caused the big mass to move a little bit, but that same collision caused the little mass to move a lot. Right? So the little mass moves backwards at a lot of speed. The big mass just kind of moves forward at a little bit of speed.
So the momentum is that 2 kilogram meters a second.
So the momentum at the beginning here was 2 kilogram meters per second. The momentum of the second one was 0. So the momentum total here was these two added together. 2 plus 0 equals 2. Right? And it has a direction. It's this way. The momentum is forward. Now the momentum here is different. The momentum here is 3 times 0.5, but it's backwards. So it ends up being negative 3 times 0.5, which is negative 1.5, right, for this guy. But for this one, it's 3.5 times 1, so this one has a momentum of 3.5. And when you get the total momentum here, it ends up being, and this one's positive, it ends up being negative 1.5 for the first car, 1.5, plus 3.5, which happens to equal 2. So it's the same. It's manifested very differently, but when you add them up, it's still the same. 2 kilogram meters per second of momentum. And it's still forward because it's still positive. It's still a forward momentum because this one, even though it's moving very slowly, has a lot of mass. And so it's carrying more momentum forward than this one is carrying backwards. So the overall momentum is still forward. Okay? So momentum has just as much to do with mass as it has to do with motion. Right? Remember, energy was different. Energy was much more about velocity than it was about mass. Remember, we talked about the reason that the United States military switched from the big 30 caliber bullet to the small 223 round. Because the mass wasn't as important if you're trying to do damage. If you're trying to push people around, you want a bigger bullet. If you want them to move and to fall over when they're shot, then yeah, you want a big bullet. But if you don't care if they move and you're just trying to do damage, then scientifically this makes more sense. And once again, it's kind of gruesome, but it is scientifically sound. It makes sense scientifically. And it's been very effective. Also, you can carry a lot more bullets, right? So that's also militarily more sound. And believe it or not, it's had a huge effect on the world because of the choices that militaries make.
You know what's better than a little bullet going really fast?
What's that?
A big bullet going
Yeah,
really fast.
if you can carry it. You know, the Barrett 50 caliber
It doesn't-
rifle is
it
great,
doesn't
but
go
you
that
can only
fast.
carry 8 bullets.
It doesn't go that fast.
It can if you load it right. They can move super fast. Depends on the load. The shell on that thing is like a foot long. Well, 6 inches, but you know. You know what I mean? But anyway, the point is that it's, you know, science plays a role in a lot of things, including military, politics, war, and all that stuff. And those decisions were not made randomly.
So if we stretch this out and figure out what it would be, right, it would be mass times velocity plus mass times velocity equals E total.
Yeah. But you got to remember the velocity has direction, so it can be positive and negative. With this one, the velocity is negative, negative 3 meters per second,
Because it's a vector.
because it's a vector and it's moving backwards, right? So, yeah, exactly. So this is negative 3 meters per second times 0.5. This is positive 1 meter per second times 3.5. Is that a better illustrated narrative?
Yeah.
I'm going to make a graphic physics novel textbook.
What with a lot of cuss words and stuff in it? Or what?
They'll have a bam, zowie, and stuff in it.
English guy is coming out of the
That's right.
The way things work,
All right. All right, let's
Wake up. No.
let's look at this. The collision lab. You guys get to crash things together tomorrow for your lab. Okay, come on. Is it going to go or what? Apparently it's not going to go.
So just to reiterate, if you know the mass and velocity of the first object and the mass of the second object, you can fairly accurately predict how much momentum is going to transfer just based on the mass of the other object.
How much momentum will transfer? Yeah. That's correct. And that's a great thing, actually. Okay, so that's the idea behind elastic collisions. Kinetic energy is conserved, momentum is conserved, so you get two equations. Inelastic collisions are not going to conserve your kinetic energy, so you're going to have one less equation. But the beauty of it is the equation you're left with becomes much simpler. Why? If it's a perfectly inelastic collision where the two objects become one object in the end because they're stuck together. Two cars crash and they lock up together and they become one object. They never separate until the end of their movement, for example. Then it's called an inelastic collision. We call it perfectly inelastic. And in this case, momentum is still conserved. Now we do have to still have no outside forces. So we can't have outside friction. We can't have energy loss due to, we can't have momentum loss due to anything outside of the system, particularly friction. But the interesting thing is that the momentum equation now becomes very simple. And this is what it looks like. Momentum 1 plus momentum 2 equals momentum 1 prime plus momentum 2 prime. Initial equals final, right? Just like before. Total initial momentum, total final momentum. However, in the final momentum, our mass 1 and mass 2 are going to become the same mass. And so instead of having them separate with two separate velocities, we're going to put them together by adding them first and then multiplying them by one final velocity because it's just one object. Right? So we get rid of one of our variables. Our second final velocity no longer exists. Here's the example. We have a goalie who catches a puck. The puck is moving, it's screaming. But the goalie catches it, and once the goalie catches it, the momentum transfers to the goalie. The momentum of the puck becomes momentum of the goalie. But the goalie is holding the puck. So it's also the momentum of the puck. It's the momentum of the puck plus the momentum of the goalie combined as one thing. So the mass ends up being mass of goalie plus mass of puck to be the mass of the goalie puck, or the puck goalie, or whatever you want to call this object now, times the velocity of the goalie puck. Right? One object. It becomes one thing. So the equation becomes simple. When you solve this equation, and you can solve this equation, you solve this equation for the final velocity of the goalie and the puck combined, and this is the equation you get. The final velocity equals mass of 1, which is the mass of the puck, over the mass of the puck plus the mass of the goalie, times the velocity of the puck initially, and you're done. Now this only works if the velocity of the goalie is 0 to begin with, right? So this assumes that m2v2 equals 0. If m2v2 does not equal 0, and the goalie is moving when he catches the puck, or she catches the puck, then you'll have a different equation. But this is a very simple equation for that. All you have to do is plug in your masses, plug in your initial velocity of your puck, and you can calculate it pretty easily. Now, let's see if we conserve kinetic energy. The initial kinetic energy, 1/2 mv squared of the puck, is 91.9 joules. It's got a ton of energy. But the final internal energy of the goalie, just sliding backwards a little bit after catching the puck, is 1/2 mass of goalie plus mass of puck times this very, very small velocity squared. Ends up being 0.196 joules. Energy is lost in the extreme. You lose 91.7 joules of energy. You lose over 90% of your energy. And that's lost in the deformation of the glove. It's lost in heat. Anybody in here ever caught a fast-pitched baseball or a fast-hit puck? It actually heats up your hand really a lot. There's a lot of heat loss as you catch it. It also can do some damage to your hand, especially if you catch it wrong, but there's a lot of sound, right? And so all of those are ways that this energy is lost, and over 90% of that energy is lost. It's almost, that's actually more than 99% of the energy is lost. So the energy is certainly not conserved within the system. It is dissipated in all these different ways. So let's look at two carts that are going to collide inelastically now. Two carts that are going to, this is actually going to be like our lab. This collision is not what you consider a normal collision. We have two carts that are going to be stuck together, and then a spring between them is going to launch them apart. So it's like an anti-collision. It's like the opposite of a collision, right? It's an explosive collision, right? And this is kind of like what you'll see in your lab tomorrow. But in this explosive collision, we have the two carts with two different masses, and they're going to end up going two different speeds. Let's see here. During the collision, spring the potential energy initially compressed. So initially, I think initially they're not moving. Does that sound right? Oh no, so the mass of cart 1 and the spring is 0.35, and the cart and the spring have an initial velocity of 2 meters per second. Cart 2 has a mass of 0.5 kilograms initial velocity. So we have initial velocities of the two carts and masses. And then they're going to collide, and they'll have a recoil with velocities. They're going to have a recoil, and there's going to be a kinetic energy added to one of the carts because of the spring. Okay, so conservation of momentum is still going to be valid. So we have initial momentums and final momentums, and we end up with initial and final momentum giving us a final velocity for the second car, which is the only thing we don't know, of 3.7 meters per second. So we plug in everything that we do know, conservation of momentum is still there. However, internal kinetic energy is not going to be the same before and after. 0.763 before, 6.22 after. And that means the change in the energy inside the system is 5.46 joules. That is the energy that was added by the spring exploding the two cars away. So in this situation, you have two cars that come together, and then the spring pushes them further apart as they come apart. Kinetic energy not conserved, however, momentum is still conserved. Which seems weird because we had this spring that's going to do this, but that spring was internal to the system. It didn't transfer any momentum out of the system. So it didn't change the momentum of the system. And it is true, it will work out. And you'll see some of that in your lab tomorrow. Seems counterintuitive, but it is true. Why would that be the case? Why would we have two masses coming together at some speed, some momentums, and then have a spring that's going to add velocity to the system, and yet the momentum is still conserved? Remember, the spring is going to push the one car this way faster, but it's also going to push this car what? This way faster. So any additional momentum that this car gets, this car is going to get an equal amount of momentum to cancel it out. So the conservation of momentum is still in effect, even though we added velocity to the cars with the spring. We added energy to the system. Because the spring was internal to the system, it doesn't affect it. If we had a transfer of momentum from outside the system, that would be different. But it was not the case. It was internal to the system, so it affected both of them in opposite directions. Okay, so that is linear momentum in one dimension. Now we still have to talk about momentum in two dimensions. And this is where it gets very interesting. So we're going to play pool. I wish I had a pool table. I kind of do. Maybe I should get that. Where is it? Oh, it's over here. I haven't played with this in a while. I need my air source. I'll be right back. Okay, now the idea here is to turn that on first of all. We'll switch over to our document camera, and then we'll point the computer up there so he can kind of see when he watches this video. See if that gives him a decent view of our air table. Not bad, not bad, not bad. Okay. Needs a better background. Needs a white background. Get too much junk up here. That's better. Okay. So what this is it's a little air table, like air hockey. We'll turn it on. Oops, I need power. All right, power. Turn it on. This is like a $400 air blower. The reason it costs $400 is because it's quiet. It's the only real reason it costs so much. All right. Now we gotta adjust this thing so that it's level. Yeah, it's right there. All right. So then I can put my things on here. And we can have collisions. Kind of like a so it's two-dimensional collisions. Now these red and green guys, you can't really see the green. I'll take them off here. They're pretty much the same mass. And you can see that they have pretty much the same effect on one another. You know, if one thing has a collision with another one, the other one reacts in pretty much the exact opposite way. You can see that, hopefully. But it is two-dimensional, so it can be at angles. If they hit straight head-on, then the reaction is a little more intense. If they hit kind of at angles to each other, then it's not quite so much. This one has more mass. That clear one it has more mass, so these smaller ones bounce off it pretty easily, they bounce off of it a lot, and it doesn't do a lot of bouncing. It just kind of does its thing. Right? Let's see here. And what? Oh, here's another one. Another big one. They're just little magnets on discs is what they are. Not enough air for those ones to move really well. Turn it up a little bit. There we go. But it's just exchange of momentum. The reason that these things bounce off of each other is because they have magnets, and there are magnets around the edges, so that the magnets are all arranged so that they repel each other all the time. But that is exchange of momentum, conserved exchange of momentum. The less friction there is, of course, the less exchange of momentum that there is with the platform itself, and so you get less that broke. So that you get less of this action keeping going. But if you have a very low friction, it'll just keep going for quite a while. momentum will just change back and forth, from big object to small object, small to big, small to small. Conservation momentum. Now, let's do some experiments. Come here. Good, right. Okay. Let's do some experiments. That we've seen. We have our first object. We're just going to let it sit still here. And we're going to hit the first one with the second one. First one sitting still, maybe. Come on. Can I get you to sit still? Too much air. The smaller ones like less air, the bigger ones like more air. Okay, it's kind of sitting still. Now I'm going to bring this other one in from far away, and I'm going to collide with the second one. Try to hit it head on. Right? But what happens if I hit at an angle? Let's see if I can do it better. Right? It not only moves, but it moves off at an angle. They both move off at angles, right? And we've seen that when we play pool. We've seen that in many different situations. You hit a car at an angle, you push it off at an angle, and you go off at another angle, the opposite angle, but only in one dimension. Even though it looks two-dimensional, it sometimes is only one-dimensional. We're just not aware of it. So, that is our little miniature pool table. Air table, air hockey. When I was a lab manager as a student in the university, we made a whole bunch of these, but big size ones. They were like 4 feet by 4 feet size, maybe 5 by 5 actually. And then we'd put one in each lab and we'd put it on the floor. Actually put 4 in each lab. Put them on the floor and they'd play with them all day for the momentum lab. I've been thinking about getting more of these. They're kind of expensive. So, here's our pool ball coming in, hitting another pool ball. We're going to have one that's going to be sitting at rest, one that's going to come in and hit it, but not hit it head on. It's going to hit it at slightly a glancing angle. It's a little off center, right? It's going to have an initial momentum that all comes from the purple ball. Mass 1 is going to be moving. It's going to have momentum. Mass 2 is going to be sitting still. No momentum. So its initial momentum is just M1V1.
Are you referring to the book?
Oh yeah, sorry. So here's the purple ball coming in, hits the orange ball it hits it slightly off center. So the orange ball goes shooting downward, the purple ball goes shooting upward. Initial velocity of the second ball right here is 0. This one has some initial velocity. So initial momentum ends up being just M1V1. But they're both moving at the end. Also, the initial momentum is going to be completely in the x direction. This is the x direction, so the initial velocity is in the x direction. We have to split our momentum into x and y directions. We're back into vectors again. So we look at the momentum in the x direction first. Momentum 1 times v1x is the momentum total of the system but at the beginning, but it's also the total momentum in the system in the x direction at the beginning. And then when it splits, these both have momentums in the x direction. This one is going to have an m1 v1 times the cosine of theta 1, and this one's going to have an m2 v2 times the cosine of theta 2. They're going to be different angles. So it's going to look like this. For the x direction, you're going to end up with m1 v1, and this is all in the x direction, equals m1 v1 prime cosine theta 1 plus m2 v prime 2 cosine theta 2. That's just for the x direction. Now, in the y direction, it's going to be different. Why? Because what is the y momentum of the initial ball? It's not moving in the y direction, so it's completely zero momentum. And this one's not moving at all, so it has zero momentum in the y direction. In the y direction, the initial momentum is 0. And then the final momentum is m1 v1 prime sine theta, m2 v2 prime sine theta 2. So those have to add up to be 0. In other words, the upward momentum of this ball has to be equal and opposite to the downward momentum of this ball. Okay? So these equations are true. This equation and this equation are true for the situation where you have an object that's at rest and an object that hits it at a glancing angle. So to calculate the things you want to calculate from here, in this case we're going to have a 2.25 kilogram object sit on a frictionless surface in a dark room. Why do they say a dark room? Because this is the kind of experiment that they're doing in science today. The dark room is the atom or some other particle that we don't know what's in there. And what we do is we shoot some particle at this particle we don't know anything about. And we know the momentum of the particle we're shooting at, but we don't know anything about the particle we're shooting at. And then we observe what comes out. We observe the angles and we observe the momentums coming out. And then we can calculate what we had to begin with, right? So it's like doing science in the dark, doing science blind. You observe what you put in, you observe what comes out, but you never actually see what happens in the room. You just calculate that part. Okay? Have you all ever played a pinball machine? Anybody ever played pinball?
Yep.
Yep.
For
Right.
ping pong.
Prefer ping pong to pinball machines? Well, you know the pinball machine where you have the ball that shoots up and it goes boing, 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 all around the place. And then you have to keep it going by hitting it back into play all the time. Well, atomic physics and nuclear physics and particle physics, all these new kinds of physics out there that are kind of on the cutting edge of what's going on to discover, you know, what things are made of.
So is this a reason why like gamma rays and stuff like that, why they have a lot more momentum than other stuff?
Why gamma rays?
Yeah, like the rays that cause like the see your bone and stuff.
Yeah,
Is
those
that
do
how it
have,
kinda works?
they don't necessarily have, they have more momentum, yes, but momentum of light, which is a gamma ray is a type of light. So that's a whole different issue we'll deal with next semester. We're not dealing with momentum of objects that have no mass right now. We're just dealing with momentum that deals with mass. However, doing the experiments that they do in atomic physics, nuclear physics, and particle physics is like playing pinball with a pinball machine that's been painted black on the top, so you can't see the ball. Okay? Maybe it's not painted black on the edges, so you can see it coming out at some angle with some speed, but you can't see anything else. You can just see the ball that comes in, you can see when it comes to the edges, and that's it. And you don't know what's going on underneath the black paint. All you see is the ball coming out every once in a while at different angles. And you use that along with the equations that you've created for what you think are the laws of physics to figure out what's going on underneath it. So it's a huge amount of supposition. We assume that this physics is good. So far, it's holding up. So far, we haven't had any huge surprises. We've been able to confirm the theories that we have and the laws that we have by doing these experiments and observing the results. But eventually, I think that we're going to come to a huge surprise and say, well, wait a second, we've got a few small ones, but not any huge ones. People keep saying that they keep breaking the speed of light, but that's always turns out to be false. And so that's one big surprise people are waiting for.
It
Don't
can
think
be
about
done theoretically, though, right?
No, theoretically, it cannot be done. That's the point. By all the theories that have any kind of proving done to them, breaking the speed of light is absolutely impossible. And that's why these so-called scientists are always trying to do it. They're trying to prove that wrong. The problem is that they've never studied the theory that proves that it cannot be done, so they have no idea what they're doing. They're really just kind of lost children that are incompetent and really ignorant. That's really what it comes down to. You'll never find a physicist who's trying to prove that he's broken the speed of light. It's always an engineer who has very little physics experience, or some other scientist, quote unquote, in chemistry or something else, that says they've proved the speed of light has been broken. But they've never really studied the theory behind it. And every time somebody goes in and looks at their work, they discover that they've done something wrong because they didn't understand the theory to begin with. So understanding the theory of light is extremely important if you want to do experiments with it. And very few people understand that. It's usually just physicists, because they're the only ones that really study it from the beginning. So anyway, so here's an interesting situation. We have the 2.5 kilogram object that's going into the dark room, and it's going to strike an object that's sitting still. So the equations that we just figured out are true, and this object has a 0.4 kilogram mass. And then they tell us that the 0.25 kilogram object comes out of the room at an angle 45 with respect to its incoming direction, and the speed of the other one, the speed of that one is 1.5 after the collision. And then the other one is the one we want to figure out. We want to know its angle and its velocity after that collision. Normally what would happen in a situation like this, you would actually try to calculate the mass and the size, the mass and the radius of this. That ends up being a little more complicated for this class than we can do for this class, but this will work too. So the two equations we have are that m1v1 equals m1v1 prime cosine theta 1 plus m2v2 prime cosine theta 2. That's the x direction equation. And then the y direction equation tells us that 0 equals m1v1 prime sine theta 1 plus m2v2 prime sine theta 2. You might be tempted to try to plug one of these equations into the other and solve, and you will eventually get to this point, but it's kind of messy. The best thing to do is to take one of these equations and divide by the other. Take the sine equation divided by the cosine equation, and then what you're going to get is this equation right here. You're going to get the tangent of theta 2 equals v1 prime sine theta 1 over v1 prime cosine theta 1 minus v1. So that's a trick that you need to be aware of. You can take two equations and divide them by each other. It's perfectly legal. You divide one side of the equation by the other side and the other side by whatever. You can take a ratio and you can get good results. Once you plug your numbers in that you know into this equation, you can find the angle theta 2. Once you find that angle theta 2, you can plug it back into either of these equations to calculate V2, and you're good to go. And this is what that experiment looked like. You had M1 coming in, M1 coming out. You want to find out what V2 comes out, what angle it comes out at, and what velocity comes out for the mass 2. Now, in the case of the most famous particle that was discovered in this kind of a way, they built the Large Hadron Collider. They built one in Chicago, but it wasn't big enough to do the job, it turns out. They thought it would be, but it just wasn't. And so they built a new one in Switzerland, on the border of France and Switzerland. Large Hadron Collider. This is what it looks like. This is the size. This is what it looks like down inside the tunnel. This tunnel is, I think, maybe 15, maybe 20 feet high, 15 or so. I mean, this gives you some idea. There's a picture of somebody walking in the tunnel here somewhere. Oh, here we go. So here's a picture of somebody walking in the tunnel. So it's more like 12 feet high, 12, 15 feet high maybe. It's the height of a tall floor of a building. And this tube down here is really just it's just a long pathway for particles. And as these particles go around and around and around, they end up going through, they go around in both directions. So they send particles in both directions. And then these particles are always colliding into each other, running into each other all the time. But at some points, they have these big detectors. So here's one of them. The most famous one is this one. This is the Alice detector. This one is like 6 stories tall. So the tube goes right down the center of this, And as these particles are colliding and goes through this big detector, every different layer of this, and you can see the different layers here, every different layer is a different layer of different detectors that detect different things. That some of them detect energies, some of them detect momentums, some of them detect angles, some of them detect, certain kinds of particles, others detect other kinds of particles. But they're all different kinds of detectors, and they're looking for particles. This is what they get. This is the actual raw data from those detectors. This is the paths of all the particles they detect. Notice that some particles they detect at the very center and they move all the way out. Some particles they only detect as little blips here and there. Doot, 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 doot. Some of them they detect, this one right here is kind of a curlicue going this way. It's moving in a spiral shape and off in a funky direction. Some of them they detect, the detection doesn't start until out here. You can't really see any of them, but they get lost in the noise. Like one's right here. One doesn't get detected till right here, and then it turns back towards the detector and goes out and stops right there. Because only one part of that huge detector can detect that particle. And so it only gets detected in that portion of it. And what they're doing is they're looking for specific signals in this detector. When they first built it, they were looking for a specific set of signals that would correspond to a particular particle that they had a theory about. And it was the theory was this particle called the Higgs boson. They have this theory that's all about all these particles that make up everything in the universe, and the one particle they'd never detected at all was the Higgs boson. And that would be the particle that was responsible for giving things mass. It's responsible for the fact that mass exists in this theory. And so they said, well, if we can get the right conditions, the right amount of energy, and hammer these atoms together, we should be able to detect these particles. So this is the black box. This is the black room, the dark room. We don't know what's going on, but we're looking at things coming out of it. The dark room is where they collide here at the center. And these are all the things that come out of the dark room. A much more complex picture, a much more complex experiment. But in their very first run that they did, they detected the particle. Probably it was the big, to date, at that time, it was the biggest, most expensive scientific project on the planet. And that's really saying something, because there have been some really big ones.
Probably still is, isn't it?
I think there's a bigger one since, but because I think right now LIGO has now reached higher, the one that detected the gravity waves, because there's several different facilities instead of just one. I think it's actually reached higher, but it's not just by one. It's not just in one place. So.
The ITER reactor was catching up on that number for specs.
No, ITER held the record before the big laser in California was built. So ITER is a plasma reactor for fusion, cold fusion. It held the record at something like $5 billion, and then the one in California jumped up to $15 billion. This one topped $20 billion or something, and I think LIGO's up around $25 billion.
So,
that's right, and it's just chump change. $25 billion is not even. It's not even a drop in the bucket in the economy of the United States. In the amount of taxes that the federal government collects and the amount of money it spends, it's not even a percentage point. It doesn't even calculate. You won't even notice $25 billion. It's just whatever, chump change. I mean, when you're talking trillions of dollars, hundreds of trillions of dollars even, for the budget for the United States government, doesn't even factor in. And most of that money is just goes to social programs. 70% of the money of the federal government just goes into supporting the people of the United States, which is fine. That's not a bad thing. But people complain about increasing the budget by 10% for science, and you don't even notice it. You wouldn't even feel it. You wouldn't feel it in the taxes. If you increased by 1% the social programs, it would bankrupt everybody in America. We could not afford it. We put so much money towards that. And we don't even put as much money towards it as the rest of the world does. Because we're so wealthy, we don't have to support the people of the United States so much. So we really don't have anything to complain about. I mean, what are the taxes in Serbia? They're high.
Yep.
Yeah, and the people in Serbia are not as wealthy as the people in the United States. And their taxes are much higher. So we don't have anything to complain about when it comes to taxes. We should be grateful that we pay so little that we do. And we have still so much left over to do so much stuff with science. So it's a good thing. Oh, yeah, it would be great if they increased NASA's budget by just, if they just doubled NASA's budget, which would not be very much. We could go to Mars in 5 years. We would have definitely enough money to do it. And add that to the European Space Agency and the Japanese Space Agency, because they would all be involved with that. We would definitely have enough on the Russian Space Agency. We would have enough money to go to Mars just if NASA increased theirs by double.
So who designs the experiments that happen to this hot around?
Oh, goodness. Well, here's one small group. This is just the group this is just a portion of the group that's in Switzerland. I mean, here you see more of them. If you see the whole group, let's see if we can find a picture of the whole group. It's thousands of people. So, if you look at this is a partial. This is just for one of the detectors there. I think they have 7. This is the Atlas experiment group. But each detector has its own experiment group. And then if you go down to UNL has a group that does experiments on CERN. They do them completely remotely, and they actually control it over the internet. So they do the experiment completely remotely, and they take their data remotely. They have their own group. It's dozens of people up there, and maybe even 100 people in UNL. They have at the University of Nebraska Boulder, they have one of the biggest groups. Wisconsin has one. University of Maryland has one. UC Berkeley. Half the universities in the world have a group working on CERN. So it's just numbers in the thousands of physicists and engineers that are doing research out there. It's just huge. It's a big deal. You guys like rap music? You gotta love this. This is the nerdiest song ever written. Nobody in this video had any business doing rap.
They got MC Hockey.
Okay, I'm getting bored of this, but if that doesn't ruin all rap for you, I don't know what will.
Reminded me of a late 80s public service announcement.
Anyway, that's what you do when you've got, 2,000 scientists, all physicists and mathematicians and engineers all in one place and hardly any cultural diversity. Anyway. Okay, so anyway, that's conservation of momentum in 2 dimensions. One of the things that's very useful for this is that you can discover more things about more properties of an object. For example, you can determine shape of things from the angles that things come out. So you can start to know, shape is a bad word to use, but you can learn more of their properties is a better way. But that is true from large objects to small objects with conservation of momentum. Beauty of it. Our last subject is rocket science. Now you can say that you're true rocket scientists. So, rocket propulsion has a lot to do with conservation of momentum. And this is why, because when a rocket is lit off, it expels its fuel out the back end, and that fuel has a mass and a velocity. So it has a momentum that goes in the opposite direction that the rocket is going to go. And that's actually why the rocket goes. Because initially when the rocket's on the pad, what's its momentum? 0. So if all of a sudden it has something going out the back of it that has some momentum down, which way is the rocket going to go? To conserve momentum, it has to go up, right? And so the 2 things that you want from your fuel is a lot of mass and a lot of speed, a lot of velocity, right? You do that by creating a rocket that's going to expand and explode and jet outward really fast, but also you use nozzles. So nozzles will help with that, and we'll learn more about how nozzles work later. But as the nozzles direct the gas outward, they make it move faster and faster and faster so that the rocket has to move upward to counteract that change in momentum downward, so that the overall momentum of the rocket is still, the rocket plus the gas is still 0. So our system of interest ends up being the rocket and the gas. However, there is a different thing going on here. As the rocket expels this gas outward, it loses mass, right? The mass that was the fuel inside the rocket is now the mass of the moving fuel outside the rocket. So it actually has a change in mass, has a delta M, right? We're going to use delta M it's going to be a rate of fuel that's leaving the rocket. So when they tell us what delta M is, that will be how fast the fuel will be leaving the rocket, or how fast the mass will be changing in the rocket. And in this particular example, they're talking about the Saturn V's mass. Saturn V was the biggest rocket ever built. It was built for going to the moon. 2.8 times 10 to the 6 kilograms. And its fuel burn rate, which was its change in mass over change in time, was 1.4 times 10 to the 4th kilograms per second. The exhaust velocity was 2.4 times 10 to the 3 meters per second. And we want to calculate its initial acceleration. Well, we have an equation for that. They don't tell us where this comes from because it actually ends up coming from we have to do a little bit of calculus for this, but it ends up being the velocity of the exhaust over the mass times the change in mass over change in time, which is the change in the rate at which the fuel is burned up or leaves the rocket, minus the gravitational constant is the initial acceleration of the rocket. So we use that equation, plug numbers in, pretty simple, 2.2 meters per second squared of acceleration, and voila, you're a rocket scientist. Congratulations. Now, how do you tell the velocity of a rocket, the final velocity of a rocket? Again, it's going to involve some calculus, so they just give us the equation. It ends up being the velocity of the exhaust times the natural log of the initial mass, initial mass of the rocket, m0, and the mass of the rocket without any fuel, so m sub r. So that's the equation for the final velocity of the rocket. Now this is a ratio, so if they give you a ratio, for example down here they tell us that the ratio of the rocket to the fuel is 1/88th. So the rocket's mass is 1/88th, so in this equation you would have mass of the rocket is mass initial over 88. And you plug that in, this number in here would end up being 88. Right? So, congratulations, you're rocket scientists. And the reason the Saturn V had to be so big is because it had to go all the way to the moon. It had to carry a lot of equipment, but it also had to carry additional rockets. I mean, there was a rocket to get it into space, into orbit, and then there was a rocket to expel it from orbit to get it going towards the moon. And then there was a rocket to bring it back. Okay, because once they got to the moon, they slowed down and orbited the moon for a while, and then they had to have a rocket to get back. So it was essentially carrying 3 separate rockets in a total of 5 stages, I believe. But three separate spaceships, rockets that would have 3 different functions. Well, in addition to the lander, the lunar lander is its own rocket because it had to land, used rockets to land, and then it used rockets to take off again from the moon. So there was 4 or 5 different rockets on there with several stages of rockets included. So much more than the space shuttle, which just went to orbit and fell out of orbit. So
We sent any people higher than basically like over orbit in the last 30 years?
well, the space shuttle has been at different levels of orbit to put different things into space. So yeah, the space shuttle wasn't only put into low orbit; it was put into because it had to release different satellites at different levels for different reasons, lots of different things. So
I know the ISS is actually pretty low,
yeah.
just outside the atmosphere.
All right, so that takes care of chapter 8. We'll move on to statics and torque for chapter 9, and then chapter 10, of course, we will crank out as well. Let's try to cover chapter 9 on Thursday this week. I'm going to, help you with homework, but if we can get to chapter 9, let's do that. And then we'll try to have chapter 8 and chapter 9 due. I'm actually going to move chapter 8 up to Friday and chapter 9 up to this one here, and try to get chapter 10 cranked out earlier too, so that we can try to move on to our later chapters. We're going to try to crank out these next few chapters fairly quickly. Chapter 9 and 10 will probably that'll be iffy to get those done that quickly, so we'll try to do something like this maybe. And then have the chapter 10 exam here, and chapter 11. But then we would try to make a little bit more time to get more of the chapters done at the end here. So let's try to crank out 8 and 9 in the next week. Chapter 10 will give us a little more
I'm
time.
chapter 8, and it's mostly like the questions, that's all,
Yeah, it's not terrible. It's not terrible for chapter 8.
they're all math, they're all quick.
Yeah. So it's not really difficult. Chapter 8's just using the equations we've given you. So the only challenge in chapter 8 is I think I gave you a problem that is a 2-dimensional momentum problem. So that might be a little bit challenging. Let's take a look. Whew, there's a lot of questions. Brick wall, spacewalk. Did I not give you a two-dimensional problem? I don't know. Well, anyway, we'll work on questions on Wednesday, on Thursday rather. So, all right. I will be back in a little bit for office hours. But,
I think it's the spring question. How do y'all do the spring question in chapter 7?
Let's figure it out. Turns out like 7 of the 9 answers were all basically the same number.
How do you get to one answer?
It's,
One half if I can fix, and you just need to follow because they are more theoretical than
I tried it, it didn't work.
try conversion from first geometrical potential, then from potential to work, and then due to gravity, you need to put minus sign in front of that. Really tricky. Really tricky.
Until you show me how you did it, I was like, oh, it was, I was just overthinking.
I spent more than 3 hours on that question. It's so more than 3 hours just reading. Yes. I did see it.
I'll cover question. Question from the lab. I can focus on all that. Yeah, you were working late. You're still working. Oh shit, you done that stuff now, Scott. You done that stuff. It's not funny. You're not still working on this, are you?
No, this is lab. Previous.
Grab the calculus exam tomorrow. Really pump this ball up. Really want to accurate the last day off. I'm all for one. plus potential energy equals mechanical energy, right?
Yep. And something forces. This part here. How do we figure out this? Actually, 3 hours.
I didn't get any of these. Like I use this equation right here, and I put it in.
Did you put this number or this number? First time I was put the number 6, so I use this number.
No, I put this number, but it comes out to like, it comes to a big number. I don't understand.
This is 150 joules times 0.0. You need to convert this to meters. 0.047. Doesn't need to be parts to calculate. That's 0.047.
See, I don't like trick questions. Until I understand the math, don't throw trick questions.
I couldn't understand that. I was observing differently. I get lucky. Because during my elementary high school, because it was metric system. How do you write this homework? Previous chapter.
Huh?
Homework for previous chapter.
It's a lab.
Oh yeah, but I think about that.
Fair time to follow.